Models make predictions that we cannot see. SHAP will show us how it came to be. Shapley Additive Explanations clear, breaking down the features we hold dear. For instance, side predictions mystery. What makes the result what it came to be? For example, a worker's salary above the mean. Is it age or skill or what's between? From expectations baseline that we know, which features make the prediction grow? Expected value shifted by each trait, that's the contribution we calculate. Additive feature attribution method, f hat x I minus expectation of f hat x equals sum of phi j, that's the facts. Shows us how each variable holds sway. In linear regression it's crystal clear. Beta 0 plus sum of beta j xj here. F hat x I minus expectation of f hat x equals sum of beta j xij minus expectation of f hat x equals sum of beta j xij minus expectation of xj. No complex. Coefficient size times features deviation from expected value, that's the equation. But complex models hide this simple truth. SHAP will be our analytical sleuth. Shapley value starts with marginal contribution. When we add a feature to the chain, but order matters in this complex game. Different sequences won't yield the same. Feature A, B, C in different rows. Adding A when nothing else shows versus adding A when B, C are there. Results will differ, we must be aware. SHAP breaks down every prediction, shows each feature's contribution from expected value to the real result. SHAP explains without consult. Consider the average of the marginal contribution when adding J to a subset S. Phi j equals 1 over j factorial sum over S subset j without j of ws times vsj. Ws is the before and after patterns of feature j. S factorial times j minus s minus 1 factorial v of sj is marginal contribution. G of S union j minus g of s explained for j equals a. We see S can be empty set B, C, or B, C. 4 subsets total in this case, each one shows a different face. SHAP applies this to machine learning's art. Marginal contribution, that's the start. Prediction G of S requires technique. Features not in S marginalize, we seek. Features in S fixed to instance I. Conditional on values, that's the time. Integration over probability space. For excluded features, that's our base. Loaded features locked to instant state. That's how SHAP values we calculate. step by step. V of empty, 1 plus V of 2. 1 divided by 2 equals G of 1 minus G of empty plus G of 1, 2 minus G of 2 divided by 2. Phi 2 calculations step by step. V of empty 2 plus V of 1, 2 divided by 2 equals G of 2 minus G of empty plus G of 1, 2 minus G of 1 divided by 2. Sum of phi 1, phi 2 equals G of 1, 2 minus G of empty. Following additive feature attribution without a SHAP reveals the hidden truth inside. Every feature's impact we can't hide. Additive feature attribution method. Instance prediction minus baseline set. 3 applications of SHAP we find. Feature importance redefined. J equals 1 over n times sum over I, absolute phi I, J. It chimes absolute values, since plus and minus. SHAP importance shows what's behind us. Different from PFI's approach. Prediction change by feature J. That's SHAP's reproach. SHAP distribution tells the tale for every instance without fail. Feature J's phi value spread shows contributions range instead. Order of magnitude we can see from SHAP's statistical spree. SHAP trend analysis reveals the flow. Plot phi ij as feature values grow. How contribution changes with the score. Feature J's effect we learn much more. Stratify by feature K's domain. Interaction effects we can explain. Cross variable influence clear. SHAP makes complex patterns appear.